Welcome to today's video lecture on stoichiometry. Today what we're going to do is define stoichiometry, and we are going to work through a real-life sample problem where we're working with full-scale models of things that we can imagine, because most of us cannot imagine what an atom or molecule would look like because we haven't really seen one before. So we're going to use some real-life objects to represent a stoichiometric problem, and we will solve it in a stoichiometric manner. Then lastly, we will apply this problem, these processes, to actual chemicals in a chemical reaction. All right, so let's start off. Stoichiometry sounds like this big weird word right now, but I want to define the parts of it. It has two Greek roots. First Greek root is stoichion, which means elements, and metry, which means measure. So the root of stoichiometry is our stoichion and metry. So what that means is that stoichiometry is the relationship, it describes the relationship between compounds in the reactants and the products of a chemical reaction. So using this process, we are able to do things like determine the amount of reactant that we need to produce a certain amount of product, or determine the amount of product that we are going to make if given a certain amount of reactant. So our real-world example is this is our bicycle or our tricycle problem, where if we need to make 3,000 tricycles, how many wheels do we need? In an elemental level, this means what mass of one reactant do we need to add to another to produce a certain amount of product. So again, in our real-world full-scale problem, we have Mr. Byers' stoichiometry party. Mr. Byer is going to have the most stupendous stoichiometry party of the decade. He wants nothing more than to have the most stupendous attendees. Last night, he went to the store to purchase 20 party invitations so that he could have the highest stupendousness per person ratio possible. In an attempt to best convince his invitees to attend, he has purchased large, fancy invitations, and each invitation requires 2 postage stamps. This morning, Mr. Byer checked his desk and realized that he has 36 stamps. How many people can Mr. Byer invite? All right. In order to solve this problem, just like we would solve a stoichiometric problem in terms of chemicals, the first thing we're going to do is write an equation and balance it. Before we write the equation, we're going to define a couple of terms. We're going to say let I equal invitation, and we're going to let S be our stamp. So in our chemical equation, what we're going to write is we have one stamp plus our invite to produce IS2. The subscript 2 means that we have 2 stamps combined with every one invitation. Now, in order to make that product, over here on the left, we need to have 2 stamps. The coefficient 2 indicates that they are 2 separate stamps. They are not attached on the left, but they are attached on the right. All right. So step number 2, we're going to use the ratio that they combined in to determine the maximum amount of invitations that he can send. So this ratio up here in which they combine is known as our coefficients. And in terms of stoichiometry, they're known as our stoichiometric or our molar ratios. These are the ratios in which they combine in terms of moles. All right, so in order to do this, if we start with 20 invites, 20 eyes, we're going to use this ratio of a 1-to-1 ratio to determine how many invitations we can make first. So we want to know how many IS2s. We see our ratio is a 1-to-1 ratio. So that means with 20 invites, we can make 20 mailable invites. Okay, as of right now, the most we can mail out is 20. But let's check our other reactant to see if we run out of that one first. We can't just check the one because we have a set amount of both. So where do we start? We start with 36 stamps, 36 S's. Now down below we have to use S and IS2. Now our ratio of stamps to IS2s is a 2-to-1 ratio. So that means that when we multiply 36 by 1 and divide it by 2, we can only make 18 mailable invites. So that means that the most invitations that Mr. Buyer can send right now is 18, because we will run out of stamps before we run out of invites. We see our ratio of invites to stamps is a 2-to-1 ratio. Were all of the reactants used? No. We had extra invites. Was there a reactant? Yes. We ran out of stamps. Now, since this is a 2-to-1 ratio, we need to purchase 4 more stamps in order to get our last 2 invitations out, because it's a 2-to-1 ratio. All right, now that we've seen this in a real life problem where we can imagine what an invitation looks like and what a postage stamp looks like, we're going to apply this to chemicals. Now again, the goal of these calculations, or this calculation, is to determine the amount of moles of one substance or of the product that can be made with a given amount of reactant, or vice versa, the other way around. When talking about stoichiometry, this is called our mole bridge. The only way for us to convert from moles from one substance to another in a chemical equation is by crossing the mole bridge. We will see that's very important in our subsequent notes, so let's make sure that we learn how to do this correctly the first time around. All right, so let me give you the rules while we work through. Step 1 is write our balanced chemical equation. In our first sample problem, we say determine the number of moles of water formed from 2 moles of O2. All right, so first we're going to write our chemical equation, which is 2H2 plus O2 yields 2H2O. That's our chemical equation for water. All right, step 1, check. Step 2, we are going to convert from moles of A to moles of B. Now, while we're doing this, we're going to pull out our trusty dusty unit conversion tool that we've been using. When we use that, always remember that we start with the given amount. We're going to use coefficients as ratios. And then lastly, we're going to label everything. Oops. The reason I write that in all capital letters is the same reason that your parents write in all capital letters when they text you. If you get a text message from mom or dad that's in all caps, you know that you're in trouble and they're yelling at you. So just like that, when I write that in all capital letters, I do it because I'm yelling at you so that you remember to always label all of your units. All right. Convert from moles of A to moles of B. Trusty dusty unit conversion tool. We start with 2 moles of O2. 2 moles O2, diagonal across. Our unit is going to be moles of O2. And then up top, we want to know how many moles of H2O we can form. Now, our numbers are going to come from the coefficients. So moles of O2 is 1. Moles of H2O is 2. All right. Now we can see moles of O2 is going to cancel. 2 times 2 divided by 1 gives us 4 moles of H2O. All right. Please make sure that we understand how this works and how that unit conversion tool works so that we can correctly calculate later on. This is our integral part because all roads in stoichiometry lead to the mole bridge, and this is the mole bridge. All right. Enjoy.